Alright, in this video we are going to talk about heat and heat transfer as well as how to calculate heat transfer. Before we do that, going back to energy for a second, we've had two types of energy, kinetic and potential. We've measured kinetic energy through temperature, and potential energy is involved with the bonds. So chemical reactions always involve the breaking and forming of bonds. So we're converting back and forth between potential and kinetic energy. And with reactions, they're usually classified as endothermic or exothermic, as we've also discussed. So looking at this graph, which is labeled exothermic, the reactants start out at a certain energy level. There's an initial activation energy required for any reaction to break some bonds. But then when the reaction's all done, the products are at a certain energy level over here. And if you look, the amount of energy in this system has decreased, and we would call that an exothermic reaction. So what would we see if we were to do this reaction? We would expect the temperature to go up as it's giving off energy to its surroundings. Vice versa, over in this graph we have some reactants that start out here, and then at the end of the reaction the products are up here. So the overall reaction has more energy now than it did when it started out with. So to see this, we would expect the temperature to go down. The actual solution would get colder, and we'd call that an endothermic reaction. Our two thermodynamic laws. Energy is always conserved. This is similar to the law of conservation of mass. We're never going to lose or destroy or create energy. We're only going to transfer it. The second one, the energy tends to disperse or spread out over time, which increases the disorder. We call that entropy, and we will come back to that in a few lessons. So we talk about heat being transferred. And heat itself is defined as the transfer of energy between two substances due to a temperature difference. Heat always transfers from hot to cold. So when you open your refrigerator door, and you aren't letting the cold air out, technically you're letting the hot air in, because the energy is going from the room air to the temperature in the refrigerator, the air in the refrigerator. When you're mixing two different mixtures, whatever that temperature ends up being, however much heat gets transferred, it depends on two things. It depends on the actual temperature of those samples, as well as it depends on the amount of those samples. So if we are mixing samples of equal volumes, the temperature that it'll end up at is just going to be an average of the two. So if we had 25 grams of water at 30 degrees Celsius with 25 grams of water at 60 degrees Celsius, it's pretty easy to predict that the final temperature would just be the average. It would be 45. If we're mixing water of 30 degrees Celsius, it's still 25 grams. And we mix it with a larger sample of water that's 60 degrees, the final temperature is not going to be 45 because we had a larger mass here, and that's going to have more energy to transfer to the smaller sample in this case, because the larger sample was at a higher temperature. So no, and it's due to the amounts are different to answer this question. So before we can actually calculate how much energy is transferred, or heat, you'll notice I'm using the words heat and energy synonymously. They mean the same thing for purposes of this class. Outside of an introductory chemistry class, heat and energy can have different meanings, but we are keeping the pressure the same. So heat and energy, as well as there's going to be a third word that all will mean the same thing in this classroom, and that third word is enthalpy. But before we can go ahead and calculate just how much energy or heat is being transferred, we need to define specific heat capacity. That's the heat required to raise the temperature of 1 gram of something 1 degree Celsius. Specific heat capacity I always think is easiest to describe using a swimming pool on a hot summer day. The sun's been beating down on the pool The concrete that surrounds the pool is really, really, really hot, yet the pool water is not, even though the sun has been shining equally all day on both substances. And the reason really that it has to do with it is the atomic makeup of water versus cement, or even the air is really hot, I suppose, on a summer day. But specific heat capacity is a measure of how much energy water would have to absorb to increase in temperature. And water needs to absorb a ton of energy to warm up a little bit when compared with air or cement. And the other thing on this graph is aluminum. So it gives you an idea of whether things warm up really quickly and cool down really quickly, as in the air, or whether things take a really long time with a constant amount of energy applied to warm up as well as cool down, such as water. So to calculate heat transfer, we're going to use this equation, where Q equals mCp delta T. Q is defined as heat, or energy, or enthalpy. It's measured in joules. The M is our mass in grams of whatever substance it is that is we're transferring heat to. Cp is our specific heat capacity, and delta T is the change in temperature. And it's important to highlight this one because change in temperature, specifically the final temperature minus the initial temperature, it needs to be that so you end up with either a positive heat transfer or a negative heat transfer, depending on whether you're warming something up or cooling something down. That way Q's sign is appropriate. So let's do this example problem. So to calculate the heat transfer needed to raise the temperature of 5 grams of water from 20 degrees Celsius to 30 degrees Celsius, we're going to use this equation, and here is our Cp of water. This is a constant for liquid water. This is something that would need to be given to you. You don't have to memorize that. So we have our Q equaling mCp delta T. Q is what we're looking to find. M is 5 grams. Our Cp value is 4.184. The units are joules over grams degrees Celsius. And our change in temperature, let's calculate that. The change in temperature is final temperature minus initial, or 30 minus 20. Which would be a positive 10 degrees Celsius. So we'll put 10 down there. When we multiply 5 times 4.184 times 10, we get a heat transfer value of 209. The units that you end up with, grams divided by grams, cancels out. Degrees Celsius cancels out. We're left in units of joules, which is ideal since Q is measured in joules. So that's how you would calculate heat transfer. We have one thing left. The last thing we're going to learn how to do today is calculate the heat of reaction, and I put experimental in here because this is specifically something we're going to use during a lab. The heat of reaction is on a per mass or per mole basis, so it doesn't matter how much you have of it because it's per grams or per moles, versus our heat transfer equation, looking back at it, you multiplied it times the mass of the substance, so it was specific according to how much you had of it as well as the specific temperature change. This gets that factor out of it, and you're allowed to compare it to theoretical values. So experimental heat of reaction is defined as delta H, and that's the change in energy or enthalpy, which is a word we'll use more often. And it is equal to the negative Q divided by the mass or moles, depending on whatever the problem is asking you for. In this case, our example problem is giving us 20 grams, and it's also asking for you to calculate the heat of the reaction in joules per gram. So we'll just use grams. So delta H equals negative Q over M. We are going to use the example problem from the previous slide where Q was 209 joules, and it's divided by however much fuel, in this case it's fuel, was used in the reaction. This says heat of combustion. The reason it says heat of combustion as opposed to heat of reaction is because we're burning a hydrocarbon, so technically it's a combustion reaction. In chemist way of being fancy, if you will, they tend to call it the heat of combustion when it is a combustion reaction. If it's not a combustion reaction, they'll just say heat of reaction. Thankfully, they don't get specific and say heat of the single displacement reaction. So anyways, the mass of the reactant that was used or burned in this reaction was 20 grams. So 20 grams of fuel was burned, and that's what heated the 5 grams of water in the previous example problem. So with these types of problems, you're going to commonly be given two masses. One is what's being heated, and the other one is the reaction that's actually occurring to do that heat transfer. Alright, so let's put 20 grams down here, and now it's simply a matter of dividing that out. Oops, I already got a negative sign there. So the delta H value is negative, what does that come out to be? About 10 joules per gram. And that's it.